In this video, I'm going to introduce parallel equivalent resistance and the current divider rule. Let's start out with a circuit. We have a voltage source and two parallel resistances. We'll call these nodes A and B. First off, we can observe that VAB is Vs. We can identify currents through these resistors, R1, so we'll put here I1, I2. We can see that R1 and R2 are both connected between nodes A and B, so the voltage across R1 and the voltage across R2 is also Vs, so let's just write that in here. So that enables us to use Ohm's law so that I2 is Vs over R2 and I1 Vs over R1. Just Ohm's law. We can do that because I1 and I2 are consistent with Vs in terms of the passive reference convention. The next thing I'll point out here is that the voltage source provides some current. We can write it in like this. So now let's use Kirchhoff's current law at node A. So here I'll use all currents entering the node and we'll sum them to 0. So what currents are entering the node? Well, we have I is entering the node A. We have a minus I1, right? Because I1 is leaving, so we treat that as a minus I1 that's entering. Same with I2, so negative I2 is entering the node. All of those have to sum to 0. So that allows us to write this, I1 and I2. Now, if we use our Ohm's law expressions, we have this. And then we can factor out the Vs. And what we see is that this looks like a 1 over an equivalent resistance, right? Because we have some current proportional to some voltage. We could also manipulate this and write. So our equivalent circuit looks like this. And now it's clear that we can figure out what the current is because we know the voltage across that equivalent resistor, right? Because Vs is still the voltage from node A to B in both of the circuits. So we can also use this information to find the current flowing through R1 or the current flowing through R2. Let's do R1, for example. This is from Ohm's law. We wrote this down right up above. But now we substitute our new expression in for Vs. So now the current flowing through I1 is proportional to the current flowing into the parallel network of resistors, but there's a constant of proportionality where the equivalent resistor goes on top of the ratio and then the resistor of interest, which should be R1, goes on bottom. We can do the same thing for I2. And we'll generalize this result. So we'll say that a parallel network of n resistors has an equivalent resistance like this. Or often people just write it like this. And finally, if we want the current flowing through any of these single resistors, IK for the kth resistor is the total incoming current for the whole network, total equivalent resistance divided by the resistor of interest. That's the current divider rule. We'll also talk about this in terms of conductance. So when we talk about conductance, we'll use G, which is the symbol for conductance, being 1 over R. So what we have, you can see here, this is what we would say G1, and this is G2. We could write this as the equivalent conductance, and it's just the sum of conductances. So you can think about conductances or resistances